Okay, so let's get started. I don't know why it does that. There we go. So this is where we left off last class with starting to talk about assembly and then solving a system of equations for the nodal degrees of freedom. So we went through all this discussion. Here was our example of changing coordinates. And then we were able to come up with an expression considering that the cross-sectional area or the Young's modulus or both could be functions of the length of the element or the coordinate of the element, and then similarly with the distributed force. So this is where we're going to pick up today. And essentially this is where you start to see what a finite element analysis would look like. And actually there's MATLAB code posted to the web page, which if I have time I'll show you as well, which is a mini program that solves some of the examples that I'm presenting today. So I'm going to do a few things on the board, but because some of the matrices get a little involved and detailed, and instead of just repeating everything on the board, I'll refer to the slides at certain times during the lecture today. But I will write some of these things on the board in a moment. Essentially, where we spent some time on natural coordinates, understanding how to come up with the integrals to calculate the stiffness matrix and the forcing vectors from here. So what you saw here was these lowercase letters to indicate an element stiffness matrix, an element degree of freedom vector. This is a 2 by 2, this is a 2 by 1. For this linear element that we're considering two nodes, this is the distributed force vector, the concentrated force vector, and they're all within this brace, and they're all this is a 2 by 1, 2 by 1. So this is a 2 by 1. This is a 1 by 2. Gives you back a scalar. So it's still an energy-like equation. And then you have this symbol here, which up to this point we don't know what that does. Okay. So today we're going to discuss how this assembly operator works to change this element level matrix operation to something that we can look at globally across the whole mesh. And so that's what we're talking about today. And we'll look at some examples which will hopefully make it clear. So we want a system of equations that looks like this, where we have these capital letters to indicate a stiffness matrix, forcing vectors on the right-hand side. One thing we'll talk about, which we have not discussed up to this point, is that we will get a forcing vector we'll call FG due to the prescription of displacements at nodes. That will actually translate to a vector that involves forces. You'll see pretty clearly how that works for the linear case. We'll have this D, degree of freedom vector globally, and ultimately what finite elements does for this case of the axially loaded bar for solid mechanics is we solve for D, and then from D we can calculate strain, and then we can calculate stress, things like that. So, okay, so this is what it says in words. So we want to talk about this operator A, this assembly operator. I'll just say that there are various ways of doing this. This is algorithmic, so you can imagine that there are various algorithms that you might come up with, and you may be more creative than what we're going to talk about today. But just to, let's say, have some background for some more traditional finite element treatments of this assembly operator, we're going to consider something called the location matrix, LM by Hughes, and that's what we're going to talk about now. So let's look at this, essentially this first example without going to the full boundary condition problem. We'll look at this little example first, and then we'll actually get to the purpose of the lecture. There are 3 examples posted in the notes. So first, let's motivate this here. Get some chalk. So, okay. So the assembly operator by way of the location matrix So, okay. So let's look at, consider a 2-element mesh So something quite simple, so like this. And we'll get to something a little more complicated, but I'll draw this now. So we're going to label this element 1 with a circle and this element 2 with a circle. And you can see there are 3 nodes, 1, 2, and 3. So without considering boundary conditions at the moment, we may have 3 global degrees of freedom for axial stretching of our bar, so stretching of the chalk. So we can have a global degree of freedom we'll call D1, and we're considering if the coordinate system is like this, it's positive in the direction of x, positive x. So then we have a global degree of freedom D2 and a global degree of freedom D3. With the examples we're about to discuss in the notes, these will become more precise numbers, but for now let's just call it D1, D2, and D3. We know that, which makes sense from a physical perspective, if we don't prescribe any boundary conditions, from a statics perspective, it's indeterminate. It's indeterminate. We can't solve the problem because basically you'll have a rigid body mode. If we had dynamics, we could throw this chalk across the room and that would be okay until it hits the wall, and then we'd have to do something else with the analysis. So D1, D2, D3, these are global. So global axial nodal degrees of freedom, which are in this case the axial displacements, so degrees of freedom. So we'll call it DOFs, like this. Now remember our element perspective. So our element perspective is we take out one of these elements here, let's say element 1, or so this is the global mesh. So the element is here. I'm not going to redraw it, but I will look at just one of the elements. So remember, from our element perspective, we have an element, generic element E. We have these generic local element degrees of freedom 1 and 2, local nodes 1 and 2, like this. So if we apply that analogy or that concept to element 1, so this is the global perspective here. So then the local, let's just look at element 1. It's somewhat confusing from this perspective that global nodes 1 and 2 happen to correspond to local nodes 1 and 2. But you'll see for element 2 that will be a little different. So we have a local node 1, a local node 2. But now, remember our local degree of freedom. So we're going to call this D1 for element 1 circle, and we'll call this D2 for element 1 circle. So I put the circle 1 here. We just said element E. And here in the notes, it just has a 1, superscript 1, to indicate element 1, element 1, element 2, element 2. But since I'm drawing on the board or writing on the board, I have a little more flexibility, so I'll just put the circle. OK. And so, yes?
So that second 2 corresponds to, for that element number 2 being the first local node, right?
Yes, so I'm going to draw that now. So for element number 2, locally, we have local node 1, local node 2 for element 2, but now we say this is D1, but now this is a 2, and this is D2 associated with element 2. So that's the same thing here, except that I didn't put a circle here in the notes. Okay. So what you can see is that from this mesh here, so at this global node 2, this global node 2 corresponds to these 2 nodes right here. Okay? And this global node 1 corresponds to this node here, and this global node 3 corresponds to that node there. Okay? So elements 1 and element 2 share a node, so they share a degree of freedom. Okay? And so it turns out that, as you'll see in a moment, this local degree of freedom 2 of element 1 is the same as local degree of freedom 1 of element 2, called, in so many words, D2. Okay? So with all this confusing machinery, what we eventually do is we create a matrix to hopefully make it simpler. So we create a location matrix to create a location matrix like this. So what we do, and it's right here, is it's a matrix. So what we have is we have the element number. So the element number are the columns, and the local node numbers are the rows. So the element numbers, these are the columns, the element numbers, and then the local node numbers, so the local node, so local node number, these are the rows of the matrix, indicating the rows. So we have, so for the local node number, we always have 1 and 2. For the element numbers, it depends how many elements we have in our mesh. So in this case, we just have 2 elements. So you'll see for the examples we'll soon consider, it depends how many elements we chose to divide this length of this bar. So we chose 2, but we could choose 3, 5, 10, 20, 1,000, however you want to do it. And when we get to the abacus tutorials, it'll be easy to make that change. But for specific code that you might write, it becomes a little more complicated. Point being that, what am I trying to say? OK, so what do we do? So how do we populate? So then we only have 2 elements. So we'll have element 1 and element 2, like this. And what populates the matrix are the global degrees of freedom, as indicated there. So the global DOF numbers populate the matrix. Okay? So what we do is it's as simple as this. For this one-dimensional case, it becomes somewhat a little easier to see. So we go to element 1, okay, and we go to local node 1 and local node 2, and we see what the global node numbers are, and then we put those in the matrix. So we go to element 1, column 1. We go to local node 1, and we see what the global node degree, the global DOF is, and it's 1. It's D1. So here, for local node 2 of element 1, it's global DOF 2. So we go 1, 2, as is indicated in the notes. So it turns out that this just looks similar to what the local degrees of freedom are, but it's just 1 and 2. Now when you go to element 2, it changes, because now local node 1 has global degree of freedom 2, and local node 2 has degree of freedom 3. So we put in 2 and 3 like this. Okay? That's how you start the process. So now you have this matrix, which is not complete because of the main thing being boundary conditions. We have not applied boundary conditions, but that's at least how you'll start. So when I go to the next set of notes, you'll see the matrix is going to expand to the right, because we're going to have more than just 2 elements. We'll have, I think, 5 elements, so we'll have 5 columns, but the row numbers will still be the same. Any questions about that before we get to the example? Will make it a little more clear, but that's kind of conceptually where we're going. And you'll see with the MATLAB code that's posted on the web page, you'll see specifically how this matrix is used in a programming sense. And let me see if yes, I do refer to that. OK, well, at least we will get to that today. So here's our first example. And it's taken from some notes that I borrowed from Peter Pinsky at Stanford, who developed a nice set of notes for finite elements. You'll see in this course it's kind of an amalgam of different perspectives, hues, and then some stuff from Peter Pinsky, and then some stuff I picked up from other finite element literature. But this is a nice little example, so I like to use it. Okay, so it's 1D. So now the difference is here, our piece of chalk all of a sudden has various cross sections. So remember I said we can change the cross sections. Okay, so we're going to have the first piece of chalk just has this diameter, or this width. Diameter right here. Then we're going to have this tapered part. Okay, so let me take a step back. So this little section here, I'll talk about these arrows in a moment. But this little section, we're just going to assume now there are no dimensions or anything. If you want to just assume SI, meters, Newton per meter EA, so E would be pascals, this would be meters squared, this will be meters. You can assume all those things, but for now we're not worried about units. But you will see a change in the E and the A. So this is, generally speaking, what we're assuming here is that the Young's modulus is constant and the cross-sectional area is changing. So here it's 1, the multiple of the 2. Here, because of the taperedness of the diameter or the radius, we have now a quadratic variation of the cross-sectional area. We get back to a constant cross-sectional area, but now it's larger than that. We just say it's 2. This is not to scale or anything. And then we go to even a larger cross-sectional area, and we'll just say that's 3 and 3. Okay, so you'll see here these L's. This L is the whole length of the bar, which is 1, 2, 3, 4, 5. And we happen to break it up into 5 equal length elements. It's just a choice. It doesn't have to be that way. You see there's one other thing we did that makes our lives a little easier, which is wherever we have a change in either the geometry or we have a load applied, we put a node. So that's by choice. We actually don't have to do that. There is a way to, you start to lose resolution, but it'll still work. You could have one element span this whole thing, but then you get into some strange functions because your cross-sectional area, you're integrating over the length of the element, and one part of the element has this area, the other one has that one. You can do it because you can integrate that. But for purposes of realistic finite elements, we don't expect to ever really do something that complicated. So we're going to put a node where we expect something to change. So what's changing here is the cross-sectional area. And also at this node, this arrow here is a concentrated force. So it's like if we were to glue something to the chalk and somehow be able to pull it, that would be an applied force. You can see there's an applied force right here too, a concentrated force. At the very top, you'll see we pin the left end of this bar to be 0, and we prescribe a displacement at the right to be 0.25. I'll admit this example has a lot going on in it, and realistically, you probably would not consider any loading condition like this, but it exercises a lot of different things that we want to talk about. So when you do your problem set, you'll get something a little more realistic, like a bar with one force at the end and distributed load, etc. Okay, so here's our distributed force. So this has units of force per length, or Newton per meter. You'll see it's going to be constant for the first 2 elements, and then it jumps up, and then it jumps up, like this. So there we go. And then lastly, this is our mesh. Here are our global degrees of freedom. They're potentially 6 because there are 6 nodes. There are 5 elements. You'll see here, I think for this first example, although I can show you how we can construct this, but recall that the R's, these are the reaction forces. So it turns out that wherever you have a displacement boundary condition, you will, by a result of that, you will have a force that you can calculate. Okay? So that is actually a post-processing step. We'll see how that works. Any questions about this so far? Let's see what the next slide is, and then we'll keep moving. Okay. So let's talk about the boundary conditions. Then we will start to break up our little vectors that contribute to the concentrated force, the distributed force, just what we talked about last class. So I'm using this slide now just because it's a little easier to discuss than rather than writing these out all on the board. Recall that, well, needless to say, if we have a pinned boundary condition where the displacement is 0, then clearly the degree of freedom, well, the degree of freedom is 0. Here at location x equals 5, we have the displacement is 0.25, so d6 is 0.25. But recall that wherever we have a prescription, wherever we have an essential boundary condition, the weighting function is 0, so that means the C1 and the C6 are 0. That actually is important. You'll see how that plays out in a few minutes. So we know we have that information based on our essential boundary conditions. So, right. So at 5 and at 0. And then we have other forces going on in between. For our concentrated force, it turns out that this is not completely needed to do this, but since we're building up from this element level perspective, I'm presenting it this way, which is we have a concentrated force for element 1, which includes the reaction force and includes that 5, but we divided it equally. We divided this 5 equally to this element and to this element. It turns out that eventually that gets added together. So that 2.5 and 2.5 here, these are the same global degree of freedom locations, but with respect to the local element degrees of freedom. So eventually this 2.5 will be added, this 3.75 will be added. And you can see here that's the concentrated force, and then we have a reaction force here. Okay, so for the distributed force, it's the same function we came up with last class with respect to the linear shape functions, which we substituted into here. And we had our length of our element divided by 2, and we had our distributed force. It turns out now this is just a constant. It could be a function of the coordinate along the length of the bar. So all we do is put in 0.5. If you do the integration, you get equal forces at each node. Similarly, you go down the length of the bar. You can see as that distributed force increases from 0.5 to 1.5 to 2.5, needless to say, we get larger values here. So we're just building up our little pieces. You'll see in the code how this is actually programmed. Any questions so far? Okay. So then the stiffness matrix. So here's our generic stiffness matrix for the linear interpolations with the length of the bar h, the length of the element h, and the EA potentially varying. So for the first element, EA is 1, yes, and then it changes to quadratic. So we just substitute in 1. The length of the element is 1. We integrate this, we just get something not very exciting. And then here, if we convert our coordinate system to Cassis from x, based on what we talked about before, from the isoparametric formulation, we can integrate that in closed form. And this is just 4/3 times that. So that's the stiffness matrix for the bar, for the tapered bar. And you keep going, and you get 5 stiffness matrices. Okay, so what we just talked about now on the board with respect to that 2-element mesh, now we have a 5-element mesh. So now we have, instead of 2 columns, we have 3, 4, and 5 columns. And instead of ending at global degree of freedom 3, we go all the way up to global degree of freedom 6. So you can see how that populates along. Okay, so then essentially what we're doing manually here, but which a program will do for you, is then we use this matrix and we try to inform ourselves as to where we start to put these individual matrices. Okay, so if you look at element 1, it corresponds to these 2 degrees of freedom. Element 2 is going to correspond to these 2, 2, 3, and then 3, 4, 4, 5, 5, 6. So you'll see that, and the same with the forcing vectors. So you'll see, basically, we take this element 1, 2 by 2 matrix, we just put it into the 1, 2 spot, like that. Okay. Element 2, the 2, 3, and you just keep moving down. So you just kind of move along like that. So what this assembly operation does, and you'll see how this gets the code is always a little easy. I personally like looking at code because there's no way there can be any confusion with it. So anyway, the point being that this sort of nebulous assembly operation, by virtue of applying that matrix, you'll see how it's programmed in a moment, this gets converted to a summation. We know how to do summation with these capital KEs instead of these lowercase KEs. And the capital KEs are basically the lowercase KE put into the global location. And then you just add them all up, and you get this large system K. Okay? You'll see it's symmetric. It's symmetric for 2 reasons. Number 1, we assume the same shape functions for the displacement degree of freedom as well as for the weighting function. But also, well, here it's scalar. But for later on, when we get to more interesting materials problems, it also is eventually going to relate to what's called the constitutive model itself. But you'll notice one thing. We'll get to it in a moment. But we have a problem. This matrix is singular. So we can't invert a singular matrix. We can't solve AX equals B with a singular matrix. So we'll get to how that will not be singular in a moment, how we're going to apply our C values being 0 at 1 and 6, and also and some other things. I think, though, that we first need to apply the same thing that we just did here with stiffness, do the same thing with force. So just do the same thing with the forces, put them in their locations. The assembly operator comes to sum like this. Same for the concentrated. You'll see we get back the 5 and the 7.5. I told you that's what would happen. Eventually, what you'll see for the next example is we go directly to this matrix. We don't break it up into its little pieces. We start to gain some confidence into how to do this. Now, what I'm going to do is I'm going to write this on the board because this is, if I can fit it, actually one advantage. Let's see. I think I can fit it over here. And I want you to see, but I want it, well, some of you have it printed out, some of you don't. So I'll write it up on the board. I could get creative and put this up and just use it screen on the chalkboard. But I want you to see how this works, because this is actually pretty important. This is how, this is all behind the scenes of what finite element codes do. You don't know what it's doing, but this is where it comes from. So, okay, so recall basically the Galerkin form. So what you see here basically is this, is you, before apply displacement VCs, we have something that looks like this. We have C transpose, and we have K D, that's that, minus F sub little f minus F sub big F, all equals 0. It's still a scalar, still a scalar equation. And you'll see the C. So what this looks like then is I'll write it a little smaller on the board because I won't be able to fit it otherwise, is this C transpose is just as you see right there, C1, C2, C3, C4, C5, C6. So I'll take some liberty with the size of my writing on the board because it's also right there in front of you. So if you can't see what I'm doing here, copy that, and then actually just copy that, and then you'll see what we'll do to get this at the bottom. We're gonna cross through it. All right, so I'm going to drop down to the next line so I have a little more space. So I'm going to put a big brace, and I'm going to put my K. So I'm just going to put my K, 1 minus 1, 1, 2, 3, 4, and then minus 1, 7/3. Keep going, minus 4/3. Oh, no, that's a plus. Yeah, plus. Good. 0, 0, 0. 0 minus 4/3. I'm just writing that down on the board. 10/3. Minus 2, 0, 0. This is the most detailed one. 0, 0. Minus 2, 5, minus 3, 0, 0, 0, 0. Minus 3, 6, minus 3, and then one more column. 1, 2, 3, 4 zeros. Minus 3, 3. All right, so there's my K. Okay, my D's are unknown except for, well, we'll apply D1 and D6 in a moment. So D1, D2, D3, D4, D5, D6. Then we have our forcing vector, the distributed one, so 0.25, 0.5, 1, 1.5, and then 2, and then 1.25. And if anything, this just forces me to write it, and then we'll get to what we're going to do. Okay, so 7.5. All right, 0, R6. Okay, closed brace, and this whole thing equals 0. So this equals 0, all a scalar, still a scalar. Okay, this is 1 by 6, and this whole thing is a 6 by 1. So this is D, this is F sub little f, and this is F sub capital F, like that. No F sub G yet. We'll show you where F sub G comes from. It's actually on the board, but I'll talk about where that comes from. Let's see. So, okay. So essential boundary conditions. So essential boundary conditions tells us that, as we recall from a few slides earlier, that C1. So if you remember from your mesh, D1 and D6 are prescribed. So C1 and C6 must be 0. I'll come back to this. Let me just show that quickly. Oops, right here. So these are prescribed. This happens to be prescribed to be 0. This is non-zero. But wherever we have an essential boundary condition, the weighting function must be 0. So C1 and C6 are 0. So let's do that first. So C1 is 0. So if C1 is 0 and you multiply through this whole vector, it cancels out this row like that. Okay? Because it's 0. And C6 is 0. So when you multiply through this vector times this vector, it cancels out the bottom row. Whoops, I have to kind of jump around here. You guys see that? Just, you're doing a matrix multiplication. C1 is 0, cancels the first row. C6 is 0, cancels the last one. I should be careful here. Let me not do it on the D. Sorry. Only do it on the K, the F, and the F. So you'll see here, the R1 and the R6 are unknown, but right now it doesn't matter. They get canceled out. Yes?
Sorry, one more time. Why are C1 and C6 0?
Oh, so C1 is equal to WH at 0, and this equals 0. Why does this equal 0? It's because UH, the displacement at the left end of the bar, in this case, well, it's 0, but this, it equals 0, but that's not important. What's important is this equals some number. And the weighting function, you can think of it like a virtual displacement or a variation on the displacement field. So any perturbation on a known quantity is 0. That's what variational calculus or virtual displacement concepts from energy methods talks about. So in a weighting function sense, basically, the weighting function must be 0 wherever this is prescribed. Okay? So it turns out that C6 equals WH at 5. This equals 0 because at 5, this equals, what did we say? It's 0.25, I think. Yeah, there it is, 0.25. So this is 0.25. So this is, I'm sorry, this is D1, and this is D6. So the reason I did not intentionally, so the question, I'm sorry, I should repeat for the recording. The question was, why is C1 equal to 0 or also C6? And it's because the weighting function, these are the nodal values of the weighting function, and the weighting function is 0 where we have a prescribed displacement. That's the reason. Now, the reason I erased my chalk right here was because I did not want to necessarily say that. So what multiplying through by C1 does, it multiplies this row and this row, that row, 1 and 6 rows here, but it doesn't multiply the D. Okay, the D is getting multiplied from the right-hand side. So what we've done is we've now reduced this to a 4 by 6. Okay, and now what we do is now we can multiply through by D. So when we, in terms of D1 and D6. So it turns out that D1 happens to be 0, so D1 is going to cancel this column. But D6 is not 0. D6 is 0.25. It gets multiplied by this column, which is a stiffness. And that D6, 0.25 times that column, 0, 0, minus 3, gives you Fg, which is right here. It gives you a force. So that prescribed displacement in the context of the finite element method gives you a forcing vector on the right-hand side. Okay? So what we insert right in here is that actually this is really minus Fg. So we'll just say minus Fg is equal to 0.025 times 0, 0, 0, minus 3. Because when you multiply a stiffness, so remember, this is units of Newton per meter. This is meter. So you multiply the two together, you get newtons. You get a force. I think that's correct. Yes. And then you can move this to the right-hand side. So this gets multiplied by D6, and this gets multiplied by D1. And D1 is 0, so that goes away. So then what you're left with is you're left with inside, which is shown in the notes, you're left with a 4 by 4 matrix, which is now not singular, number one. And number two, we extracted the portion of the stiffness matrix that we needed to multiply it by d6 to give us a forcing vector.
Why is it positive in the notes if it's minus?
Reason being that this is, well, there's a minus sign here, so I'm going to write that in a second now. What we do is eventually move it over to the right-hand side. So just hold that thought for a second. So what we do then, let me rewrite it. So now if we have this reduced C and reduced D, basically we have, so now this C is C2, C3, C4, C5. All transpose. This we'll just now call our new just C. And then we'll put in parentheses, this is our new, so this is K, and this is D. And now we have minus FG, minus F sub F, minus F sub capital F. And this all equals 0. So this is now our 4 by 4. This is our 4 by 1. So this guy is D2, D3, D4, D5. So the question was, I think the question was, why did I say this was minus FG? It's because this is it's like I'm adding that negative number. I'm just going to call this minus FG. If I called that FG, then that means eventually what you're about to see is that if I called this just plus FG, that means that when eventually I do the next step, which I haven't said yet what that is, then when I move these terms over to the right-hand side, I'm now going to have a minus on the right hand. It's just purely for convenience purposes. We just want the right-hand side to be the numbers that we're going to use for the forcing.
I'm trying to get that. It's more, I guess.
Yeah, you'll see.
Just in the notes with 0.25, that term is then positive.
Yes, it's positive because you took D6 here, and this is, so for example, what this is right here, you can think of it, this KD right here, what this is it's taking this column, multiplying it by that D1, plus this column times D2, plus this column times D3. So it's, this linear algebra problem. So it's all plus. So this happens to be plus 0.25 times D6. But from a notational perspective, eventually we're going to want all the forcing vectors on the right-hand side. So we're just going to say that this is equal to minus FG, such that when we move it over to, so what will happen is then FG will just equal 0.25 times 3, which is 0.75. So that's going to be, it's just notation. It's not, if you ignored this completely, if you ignored all this notation right here, and you take this vector right here and those and you just put them on the right-hand side, that will just be the numbers that you'll use. Yeah. So it's purely notation. Okay. Right. So this was application of boundary conditions right here. So I don't want to use the element notation, so call that 1. Okay. So now we're at 2. So there's this important concept from energy methods, which also applies in variational principles, which is that where the essential boundary condition is prescribed, these must be 0. But everywhere else, they must be arbitrary. They're perturbations. So in theory, C2, 3, 4, and 5 can be anything. They're arbitrary. But this equation must be equal to 0. That's what our weak form told us from the strong form, and then from the discrete approximation to the weak form to the Galerkin, and then we did our interpolation functions. So if this equation must be 0, and this is arbitrary, then that means that the only way this equation can be satisfied is if what's in the parentheses is 0. Okay? So if C is arbitrary, okay, so we say here for all WH, so for all values of the weighting function, that's where that for all is important, then that implies that in parentheses must be equal to 0. In this case, it's equal to a vector. So this is a vector equation. This must equal to 0. So if that equals 0, and you're just based on the previous question, if you rearrange the terms, you get this. You get k times d equals f sub g plus f sub little f plus f sub capital F, like that. And we can solve that equation. That's a linear system of equations. K is non-singular. We have all the forces that we applied to our bar, and that's our solution. That's the first step of the solution. So that is the linear algebra solution, but then we do post-processing stuff. So does that make sense? That's a subtle step. First of all, the first subtle step was applying the essential boundary conditions, which did things on C1 and C6 and based on what was on D1 and D6. We applied that there. We then see that we have this system, but we still don't know what to do here. So then we say, well, recall that from our weak form, we said this in our Galerkin, this weighting function can be anything where the boundary conditions are not prescribed, the essentials. So then that means that has to be 0. OK? So that's it. So there it is. So we solved that. So we can solve that system of equations. I'll show you a little MATLAB code in a second. But basically, there's the equation. Here's what I just said in words for all w in this variational space. Oh, there's fg. There's our solution. Yeah, I mean, it wasn't set up so that these would be nice numbers. That's just those are the numbers out to significant digits, 4 significant digits like this, or the 3 significant digits with regard to the decimal. Okay, so I think I'll show you the code. So for this particular example, I forget why in this example we don't go back and do all the post-processing. We could do that. But some of the other examples, we do the post-processing where we would take these displacements, we would calculate strain, and from strain we can calculate stress. We can also use these displacements and these ones right here. We can come back to this system of equations and we can solve for R1 and R6. Once we know D2 through D5, we know D1 and D6. But rather than including all those additional calculations now, some of the other examples do that. But what I do want to show you is how we would program this, and well, doing the linear algebra is not hard, but it's just how to come up with this system of equations in a program, as opposed to just, well, we know what those are right here. They're right here. So we know these matrices and vectors, so that we can just plug that into any linear solver, and we can solve for these d's directly. But what I did on the board is not something you'll normally do. What we'll normally do is have a program that does what we did on the board. Yes?
What are the units of those displacements in relation to the lengths, which were like 1, right, for each?
Yes. Yeah. So exactly. So this is a contrived example. So it's obviously that would be a very large displacement. It wouldn't fall into small strain theory. When we go to the actual example you're going to get on the problem set, it'll be a little more. I think it's a little more realistic. But yes, to answer your question, the units are the same. So if the units of the length of the bar, so the question is this: is that if the length of the bar is 5, right? I think there are 5 elements. Then that would mean that from a physical perspective, that would mean that we would be stretching this thing incredibly, right? So like this.
The prescribed boundary condition at the end of the bar was only 0.25, so wouldn't this imply that like part of the bar moved past the end of the bar? It seems to say that. That would be what would happen. Yeah. So it's not real world application.
No, it's a contrived example. Okay. Yeah. It's just contrived. You'll see for the example for the problem set that I'll give you, it'll be a little more careful on choosing numbers. Like I said, I picked this example. It kind of was nice to exercise different things, but it's not physically realistic. Yeah. So, okay. Any other questions? Yes, there was okay. Well.
Yeah, I was going to ask something that I realized.
Okay. Okay. So let's. This is posted on Learn, and then let me see if I can find them. Where's the? matrix. Where's my thingy thing? There's the example. Okay, so here's the code. So I'm going to open it up. This is posted on Learn. It's posted as a zip file in this a zip folder. I'm jumping ahead a little bit because there's one thing we have not covered that you'll see in the code, which is Gaussian integration, so Gaussian quadrature. So you'll see that instead of in closed form programming up the various element matrices that would assemble this global matrix, you'll see an actual numerical integration technique called Gaussian quadrature. But you will see some various subroutines. This is written, it's in MATLAB. It's not very elegant, but it gives you the general idea, which is that there's an element, a distributed element forcing vector subroutine. There's the stiffness matrix subroutine when E and A are constant. And then there's one where the A is quadratic. And then there's the post-processing step for stress, which right now we haven't shown on the board, but it does the calculation. And then there's the driving code. We call it EX1 code. So let's open up EX1 code. Let's see what that looks like. And I don't expect you to understand all this stuff right now. For the next problem set, you'll be given a similar code that you will basically rerun and study yourself. But these are posted if you want to study it now. So these are just some MATLAB things. So we're clearing all the variables, setting the format to the short scientific notation, not the long. Here are the values. EA2 is 1. I said we'll include quadratic function below, but these are the constant values otherwise. We assume E is constant. The distributed force is also assumed to be constant in each of the bars. So you have 1 through 5, each of the elements, I'm sorry. And then the stiffness matrix. So what we do is, and this is where a meshing program would come into play, something related to maybe a CAD program as well, is you would have coordinates of your nodes. So here what's happening is this is a 2x1 or a 1x2 vector. It's just a storage. So for element 1, it's 0 and 1. For element 2, it's 1 and 2, etc. So what these coordinates allow us to do is that HE, which we just assumed it was 1 for all the elements, this will get calculated from the coordinates. Okay, you'll see that in the subroutine. So all that the stiffness matrix subroutine needs, it needs the coordinates of the element nodes, and it needs the value of the E and the A. So let's look at the first one, which is just constant. And then, so I'm trying to remember what I opened. Will it remember where I am? Yes, okay. So it gets passed into the function. Then locally, it'll grab those nodal coordinates and just store them as local coordinates x1, x2. It'll calculate the length. There you go. It initializes the stiffness matrix. It's a 2x2 matrix. Here's the Gauss quadrature, which we haven't covered yet. But for right now, it turns out that for this simple problem, the numerical integration is exact. We'll get to this in a moment. I mean, we'll get to this. I'm not sorry, not today. We're not going to have time today. But maybe next lecture, you'll get to this. Is that so? This loop through the Gauss points refers to our integration. So for those of you who are familiar with Gaussian quadrature, the integral can be approximated as a sum over the integrand evaluated at that coordinate multiplied by the weight. So it turns out that the coordinate, in this case, I forget why I used 2 integration points. It's actually not necessary. 1 would have been sufficient, but it's programmed to be 2. So what you're seeing here is that if this is our local element, and this is x1e, this is x2e for element e, and then this is obviously node 1, and this is node 2. Our natural coordinate c is in the middle, and there are 2 Gauss points, or Gaussian quadrature points, one here, one here. This is at minus 1 over root 3. This is at plus 1 over root 3. And the weight of the integration, again, for those of you who haven't seen this before, don't worry about it. We'll get to this in more detail. But the weights here are just 1. So what you do, and then remember that our Jacobian of coordinate transformation, for this particular case, we formulated this ourselves, so it's just directly programmed. It's the length of the element divided by 2. so that you're going to see that JE come in. And then the strain displacement matrix is just negative. It's 1 over the length, 1 over the length. We have that. So we do the B transpose times B. We have EA. So this is our integrand right here. Okay? That's our integrand, which includes the J. J happens to be constant, and there's our weight. And it turns out that all of these values are constant, except that for the next problem, the next element that has a quadratic cross-sectional area variation, this will then be evaluated at the integration point. Oh, I'm sorry. That must be why I chose the Gaussian quadrature of 2, is to integrate that exactly. Now I'm trying to remember. Because if the area were constant, a 1 Gauss point would have been sufficient. So you see that basically you assemble the stiffness matrix as basically as the value at 1 Gauss point plus the next one, and you get KE. Okay? So that is how you would assemble one of the constant cross-sectional area ones. Let's look at the quadratic. And then more important, I don't want you to worry about those details right now. What I want to focus on in this code is to see how this is done from a programming perspective. Don't worry about these details for right now. We'll get to the Gaussian quadrature later. So let's just look at the quadratic one just so you can, just because we have it. So it's the same procedure, except that, remember I said, for the isoparametric formulation, it's the x equals the shape function times the coordinate of the shape function 1 times its coordinate plus shape function 2 times its coordinate. But this is evaluated at c, which happens to be at minus 1 over 3 and 1 over 3. Again, don't worry about that. But then that will get fed into the quadratic function, which then gets fed into the integrand, and then you're just integrating that directly. So this will be our integrand. So EAX is to indicate that E and A is now a function of x. It's really A is a function of x. E is just constant. So it's the same. It looks exactly the same, except that this can be a quadratic function. Okay. Now let's focus more. And there's the same thing for the distributed force vector. So you can check this one out if you want. So the same looking like thing, except here's your transpose of your shape function matrix N1 and N2, and everything else is the same, F, etc. So you can study these later. Let's look at the main code. That's what we want to focus on. So where is it? It's back here somewhere. Okay, so let's say that, again, this is not done in an elegant manner from the perspective that you can see that every stiffness matrix is evaluated by a separate line of code. Needless to say, you would have some more sophisticated loop or something else that you would be programming that would make this a little more fancy. But what you do see is that the same analogy here is this concept of capital K. So I take lowercase k1 and I store it for now in a capital K sub k in storage location 1. The nice thing about MATLAB is you can keep appending, as many sort of storage locations as you want. We're not going to operate on this K sub k. We'll operate on how this contributes to the big one on the board. But you do this for all the so we have 5 stiffness matrices. You do the same for the force vectors. And again, we store these in the capital F sub F. And then I think we have, OK. So then what you'll see here is that we define, or we know a priori, what our global degree of freedoms will be, which will only be 4. It happened to be 2, 3, 4, 5, 6. I'm sorry, 2, 3, 4, 5. Turns out that in a code, we're not going to use 2 through 5. We're going to use 1 through 4. Okay? But for purposes of illustration on the board, I call this 2, 3, 4, and 5. You'll see in a moment that the D1 and the D6, we don't actually typically store those as D1, D6 in a code. So what I mean to say by that is that K, so here we go. We initialize again. So this will initialize to a 4x4 matrix. Our FG will also be assembled. F sub F will be assembled. F, so capital F, we're just going to discretely put in the numbers. So 5, 0, 7.50. Just, we know what nodes, what the concentrated forces are. So here's where we do the assembly. So the whole point of this is to get to the next part of this code. Okay? Okay. So you'll see one, I erased it already, but you'll see one difference from what we presented in the notes versus what's in the code. and we'll discuss this in the next example, which is this, is that in something called the LM matrix, the location matrix, which we just discussed, wherever we have a prescribed degree of freedom, we just put a 0, okay? Because it's not going to be an unknown quantity. So we put 0, and then we number from there. So we go 1, 1, 2, 2, 3, 3, 4, 4, like that. So this is still element 1, 2, 3, 4, 5 for the columns. Now, one other matrix that you're seeing here, and this actually the nice thing about this is this applies to nonlinear problems. This applies to the heat conduction problem we'll get to next, where instead of a displacement, this will be a temperature. But the same thing works out, which is this. So what happens in this assembly process, the way I programmed it, is that if you find a 0 here, it goes to the G matrix, G as in essential boundary condition, and it looks for a number. And it turns out that at this location 1 of local node 1 of element 1, it's 0. D1 is 0 right here. But D6 is 0.25. So you'll see in this location right here, there's a 0.25. Okay, and then, so then this is the local degrees of freedom. There's a little more detail. It takes some more time to study this, but this is a code. So what you do is then you loop through the elements. You loop through 1 through 5 number of elements, and then you check your LM. So you go pull out the column, and then you loop through the column, number of element degrees of freedom. You pull out the degree of freedom number. If it's greater than 0, you start to assemble. You start to add the local concentrated force to the global concentrated force vector, and similarly you go into the stiffness. So you take the local stiffness matrix and you add it into the global positions of the positions of the global stiffness matrix. And similarly for FG, you pull out the G value and you multiply it by the stiffness to give you a force, just like we did here, like this. Okay, but the nice thing about this code is it's set up generally so that instead of you wanting to use 5 elements, you wanted to use 100, you could do that. Now the complication with that is the way this code is set up is that either you'd have to generalize what's done above in terms of assembling all the individual stiffness matrices, which you could do, but this would still work. Okay, so when you come out of that assembly process, then you have your total forcing vector F. You have K, and you can just say D equals K, the backslash F, do the linear solve. And something we haven't covered yet, we'll get that to the next example, so we'll stop here, not for the lecture, but just with regard to this example, and we'll see, we'll talk about that other stuff later. But basically, if I run this, so let's run it, and see, there it is. Okay. So basically, this formed K. That has already calculated the stresses. So there's your D. So that's how we came up with the values in the PDF file right here. So there you go. Okay, so I realize that's a lot to absorb right now, but I just wanted you to see that what we've been doing up to this point can work like this. Or if you want to do, I think what's at the bottom of the code, let me just go back there. Yeah, I think at the bottom of the code is just the direct way. So what I just presented to you is sort of a very simplistic way of looking at how a real finite element code might work. But if you directly wanted to program what we did on the board, you just do these 3 lines at the bottom. Okay? So that's another way of doing it. However, this is not how finite element codes work, so we don't do it that way. But if you wanted to do what I did on the board and just use MATLAB as a fancy calculator, then that's what you can do. Okay? K, F, D. Okay? Any questions about that to this point? So there's a working finite element code that you can study yourself. Let's go back to the PDF file. And that's learn.colorado.edu. Okay. Now, with that example, we want to now, what I, in a sense, showed you in the code, what was happening, is what the next slide is going to talk about. General procedure for finite element assembly. So some of what I just talked about in the code is essentially what's summarized here. And I'm not going to rewrite this on the board. So discretize and assign node and element numbers. Actually, that's step one. There is some, well, in a commercial package like Abacus, this will be done, you'll see this will be done automatically for you. But if you were to do it on paper, you would have to do 1, 2, and this 3 right here. You would do that on paper, and then you'd let the code do this. Well, unless you wanted to do this on paper yourself, like we did here, or you could ignore the code completely and just jump to how you solve KD equals F. But even what I presented in the code, I still did some things on paper. I still took my bar and divided it. Well, you saw we already did it in the notes, how it was divided into 5 elements, etc. But the general procedure for doing a finite element assembly process is this, as I just described. So you discretize, assign node and element numbers, assign degrees of freedom, create your LM, and then you prescribe your fixed displacement, cancel rows and columns. If this is equal to 0, where you have a prescribed displacement, cancel the row, but take the column. So that's what it did here. So C1 canceled the row, and D1 canceled the column, but in this case, D6 canceled this row, but I'm sorry, C6 canceled this row, but D6 pulled out that column. Okay? So D6 pulled out that column to give you a forcing vector associated with the applied displacements. Once you have that all done, you have KD equals F, and then we do some post-processing. So it turns out that for these types of problems, oftentimes when you're designing, like stretching a bar, you're not as much interested in the displacements as you are in the stresses. So that's why sometimes finite element method is called a stress analysis, is because we want to find the stresses. That's actually ultimately what we want. Okay, so we should be able to get through the next example, which is similar to the previous one, but we're going to just apply directly what we just talked about there. So it's more or less repeating. I'm going to go through a little quicker. You can refer to these notes yourself. The second problem set will give you an opportunity to do this in more detail, with time associated with the example. So similarly, we have some things here. Now the one difference you'll see is this element's a little longer. Element 1 is 4 instead of 2, but the rest are 2. The E and the A are constant, so E8, A1. These all have zeros at the various locations for displacements, and then we have concentrated forces. We have reaction forces, things like that. So you can see how this is all going to work out. In this case, all the D's are 0. So, it doesn't matter. The C's will be 0 anyway. C1, C4, and C6 will be 0 where these are 0. We have our concentrated forces just directly. We can come up with our stiffness matrix. Here's our constant stiffness matrix when EA are constant. E and A are both going to be equal to 8. The first element will have a different length than the other ones, so we'll have to account for that here. And we do the same thing we did before. So here's our location matrix, except it looks a little different, again, than what I presented to you in the code, because the code would have zeros where we have prescribed degrees of freedom. But the general idea is the same, where you take the stiffness matrix local, put it into the global location, and you can add those all up. Here, again, this is singular. Here you have the reaction forces. You apply that procedure I just described. So at 1, 4, and 6, we cancel those rows and columns because all the D's and all the C's are 0 there. So we cancel out column 1, column 4, column 6. We cancel out row 1, row 4, and row 6, and we end up with this 3 by 3. Similarly for F, this gets canceled. This is the row because that's a transpose. We end up with just 7, 12, 25. Here there's no distributed force, and we can solve for D. Okay, so similarly, based on a recent question, we get some arbitrarily large values of displacement. So this would not fall into a small strain assumption, but for illustration purposes, this is just what we have. Okay. So I think was it this one or the next one? Okay, now we talk about stresses a little bit. So, okay, so here I do want to spend a little bit of time to review. So let's say we now have our displacements, and the calculations are there, but I'm going to do it on the board because this will be part of one of your future problem sets. And when you see a program like MATLAB, you're going to see, Abacus, you're going to see exactly how this works out. And you'll see, and this will be important from a convergence perspective. So post-processing for stress. So post-processing for stress. So recall Hooke's law. So we have sigma equals E times epsilon. So in a discrete sense, it's sigma H equals E times epsilon H. Okay, this is discrete. Or over an element E. So element E, this would be, as it is in the note, sigma E equals E times epsilon E. Don't confuse this with, when we do plasticity theory, we call this an elastic strain. That's not elastic strain. This is element E, and this is element E, like this. Okay, so we showed that the strain, so the strain in element E, okay, is this. Let's call it this. And it's just equal to our strain displacement matrix BE times DE, like that. So this will give us back a scalar equation. So this is a 1 by 2 times a 2 by 1. I'm sorry, yeah. 1 by 2 times a 2 by 1. So we just have negative 1 over HE, 1 over HE, the length of the element, and then we have local degree of freedom D1E and D2E. I'm not going to go back to the MATLAB code, but if you study that MATLAB code, what you'll see is that what happens is at the end of the code, we take the global degree of freedom vector D and we pull out the degrees of freedom as they associate with the elements, and then we do this calculation in the element. Okay, so this sort of post-processing step is done in all the elements. So basically, in a nutshell, you pull out the global degrees of freedom and you feed them back locally, and then you do this calculation. So what that calculation is shown here. So needless to say, if you just multiply this by Young's modulus E, you'll get stress. So in the stress in element 1 is E times this. So the length of element 1 was 4, and it turned out that the first node was fixed at 0, and the second node is D2 from our solution, which is back here. So it's right there. So we just put in 3.25. Okay, so if you do that math, you'll just get 2 times D2. You'll get this. That'll be your stress. And okay, so yeah, actually we'll attempt to plot this as well. So then you just apply that procedure throughout the whole problem. So element 2, same thing, length 2, these are the degrees of freedom locally. So global degrees of freedom 2, 3 go into these local locations, and you just go down the list. Okay? And that was programmed in the MATLAB code if you're interested in looking at it. If you want to calculate force in an element, note that one thing. Remember, this is a linear interpolation. Here, the displacements are interpolated linearly. Because there are 2 nodes, we have these linear shape functions, like this was N1 as a function of Cassie. So the derivative of that is a constant, so we get a constant strain, which means we get a constant stress. So this also means that if you want to calculate force in your element, given the cross-sectional area, you could do that too, but the force will be constant also. Okay? So you can see how the finite element method approximates something. So for certain instances, not only the values of the displacement for this example happen to be somewhat non-physical, but this constant stress and constant force may also seem non-physical. However, what we'll see, and it's more clear in the Bechtel lab when we get to the abacus tutorials, is the key point is that as we make these elements smaller and smaller, you'll start to see a convergence to what the solution really should be, the exact solution. That's the key point. This mesh is rather coarse, but as we make the mesh finer and finer, we'll eventually converge to the exact solution, if it's linear. Of course, if it's nonlinear, all bets are off. So, okay. So anyway, so I think we don't have enough time. So I'll just state something in words, and then you'll consider another example, and you'll also do this drawing on the board. So next class, you're going to draw what the displacement solution looks like, and what the stress solution looks like. And then, like I said here, plot here yourself so you can see what it looks like. And then, because you will be asked to do that on the problem set as well. But I just wanted to show some notes. This is just for your own interest with respect to what I just said. Irrespective of convergence, we still solved this equation. So one question may ask is, the internal axial element forces N do not equal the applied nodal forces. Okay, so we had 7, 12, and 25. So if you were to multiply these stresses by the cross-sectional areas to give you force, you may say, well, but we're not getting back this 7, 12, and 25. So the essential boundary conditions are satisfied exactly, but the natural boundary conditions are satisfied in a weak sense, in an integral average sense. So you can check this page more yourself. You can check the math. But remember, this is the equation we solved. Okay? So we solved this integral from 0 to 12. If you want to now think about it over the whole length of the bar, these are the derivatives. On the right-hand side, we had the weighting function evaluated at 4 times 7 plus the weighting function evaluated at 6 times 12. It's like that. Okay? So now if you consider that we know the values of stress, the stress is EA du dx, and we can substitute into here. Now we have the derivative of the weighting function, and we have the C1 values. And the C values are also on the right-hand side. This is C2, this is C3, this is C5. They're arbitrary. Okay? But now let's say we're coming back to see if the equation was actually satisfied or not, given the stress. We now know the stress. So if you substitute this all in, 6.5 for stress here, minus 0.5, minus 12.5, etc. If you carry through the integrals in the math, you'll see that we do satisfy that equation. So we are satisfying the application of the natural boundary conditions, the forces at those locations, 7, 12, 25. Those are the forces at locations 4, 6, and 10. We are satisfying that equation. In a weak sense, we're satisfying that. Not exactly, but in a weak sense. So if you use more and more elements, so instead of using 5, you used 5,000. Yes, then eventually, it won't be exact, but eventually those forces will start to get closer and closer to the prescribed forces. That's what convergence tells us. So we're just finished. Next class, I'm actually traveling for a review meeting this week, but my PhD student Farhad, who's here, he'll be giving a lecture next class. So please be nice to him. And let's see. So he'll cover this, and then he'll cover the next example, and then you'll continue after that. Okay? So we're finished for today.